Okay, let's take some attendance. Okay, now you can click. And you'll want to keep your clicker out today. There are quite a few clicker questions in today's lecture. Hey, do we have everyone? Last call? Good. Okay, we have promised that we would work problems with magnets, and we just kind of put that off over and over again. We're finally gonna get there. We have this problem here where a paper business card of mass 25 grams is held to the face of a door of an office-sized refrigerator by a magnet of mass 50 grams. The business card and magnet are at rest. Draw free body diagrams for the business card and a separate one for the magnet. Now, I'm gonna work this problem as an example of problems that involve magnets. It looks like someone's been here before. Okay. Okay, let's start with our picture. We've got the refrigerator. We've got the business card. We've got a magnet. And we are told that the mass of the business card, 25 grams, the mass of the magnet, 50 grams. And we want to draw free body diagrams for both the business card and the magnet. Okay. Now I told you to always draw the simplest free body diagram first, the thing that's touching the fewest other things. So in this case, that would be the magnet. So the first force I put on any free body diagram is the weight force, straight down to the bottom of your page. And that I would just take the mass, 50 grams, multiply it by 10 newtons for each kilogram, and that gives me 500 newtons. Wrong or sick and wrong? Yeah, sick and wrong. What did I do wrong? Yeah, we've got to have this in kilograms if we're going to use 9.8 newtons for each kilogram. And so I have to convert these by moving my decimal place 3 places to the left. So this would be 0.025 kilograms, and this would be 0.05 kilograms. I mean, 500 newtons, a newton's only a fifth of a pound, but that's still a 100-pound refrigerator magnet. I don't have any of those in my home. You probably don't either. So let's do that again. That's going to be 0.05 kilograms times 10 newtons for each kilogram. And that's going to give me a half of a newton. And that makes more sense. That makes more sense. Then I ask, are there any magnets in this problem? Yes, finally. Okay. And we're treating magnets just at the level of a refrigerator magnet being attracted to a refrigerator. And since we're looking at the forces on the magnet, that's going to be a force towards the refrigerator. And so I would put a magnetic force by the refrigerator on the magnet. And then I would ask, is anything touching that magnet? Well, yeah, the business card. Does it push or does it pull? Not a string, not a thread, not a chain, not a rope. So it pushes. Whenever one thing pushes on another, there will always be a normal force. This would be the business card on the magnet. And by normal, we mean perpendicular to this surface between the business card and the magnet. And since the business card is on the left of the magnet, a push would be to the right. Whenever one thing pushes on another, there will always be a normal force. There may also be a friction force. That friction force has to be parallel to the surface of the refrigerator, and I need a force that way, okay? Business card on the magnet. Now, my advice to you is if you've got a static friction force, always save that till last, okay? And then when you're deciding what direction to make that force point, ask yourself, what do I need on my free body diagram? What do I still need to make this diagram scream, in this case, 0, okay? Because I know that the magnet's not moving. So my free body diagram's finished. So now I go to the business card and I draw a weight force, Earth on the business card. It's got half the mass, so it has half the weight. And then I ask, are there any magnets? Yes. But are there any magnetic forces on a paper business card? No. Okay, so what touches the business card? Well, the magnet. Well, let's use Newton's third law. If the business card is pushing to the right with a normal force on the magnet, then the magnet must be pushing back just as hard with a normal force. And I would put a tick mark here and a tick mark there to show that they are part of a match set. Likewise, the business card cannot push up with a static friction force on the magnet without that magnet pushing back just as hard with a static friction force on the business card. And I would put 2 tick marks there and 2 tick marks there. The other thing touching the business card is the refrigerator, and it pushes with a normal force. And I also need a friction force, a static friction force by the refrigerator on the business card. Now, anytime I draw a free body diagram, I get to use Newton's second law twice, once in the y direction and once in the x direction. In the y direction, well, I know that there's no acceleration in either direction, so the diagrams have to screen balance. Since I've got half a Newton down, I've got to have half a Newton up. And because this is a third law pair, this would also be half a Newton. Because I've got 0.25 and 0.5, this is going to be 0.75 Newton. Now, I'm not told how big the magnetic force is. If I was told that this was 4 Newtons, I just made that up. This has to screen balance, so this would be 4 Newtons. By third law, this would be 4 Newtons, and this would be 4 Newtons. Yes, sir.
What is the difference between those two?
Ooh, 1 second.
What is the difference between those two free body diagrams?
When you say difference,
Like what is the key? Like what's the difference between those forces and those forces, like relative to the object that we're talking?
boy, I'm just not understanding your question. These are all the forces that are actually acting on the magnet, and these are all the forces that are acting on the business card. And you see, the way you check your free body diagram is that if this is representing the business card, this will be the refrigerator on the business card, on the business card, on the business card, on the business card, on the business card.
Show that there.
Okay.
How do you know that there is a friction?
I'm sorry.
How do you know there is a friction force?
Oh, I follow the recipe and I say, Okay? If the business card is pushing on the magnet, there will definitely be a normal force. Always, always, always. Anytime one thing pushes on another, there will always be a normal force. There may also be a friction force. That means I've only got one more force in my quiver to put on this diagram. And it's got to be parallel to the surface, which means either up or down. If I didn't have it there, this diagram wouldn't give me zero acceleration. And we're told in the problem, nothing's going anywhere. Okay, so that means I have to have this friction force. That's why I always save that friction force for last. Which direction do I have to point that force to make my diagram scream when it's supposed to scream? Now, let me point out that if I had a magic knob on that magnet that I could turn and make it a stronger magnet, well, this magnetic force would get bigger. And by Newton's second law with zero acceleration, that normal force would have to get bigger in turn to balance it. By third law, this one would have to get bigger. And by second law with zero acceleration, that one would have to get bigger. But the vertical forces wouldn't change at all. I mean, the weight's not going to change for that magnet, and the weight's not going to change for the business card. So I want you to notice that the friction force between the refrigerator and the business card is actually supporting the weight of both. Okay, that's the weight of the business card and the weight of the magnet. And another thing I'd like you to recognize is that if I could buy a refrigerator that had a perfectly frictionless surface, there's no magnet strong enough that would hold up your artwork. It'd just slide down to the floor, okay, which is where my artwork always belonged, just right down there. Are there questions on this problem? The only thing new here is that magnets attract some metal, okay, and so the magnetic force is going to be towards that metal.
Since you increase the normal force, wouldn't that increase also the friction force because you multiply?
No, because this is not kinetic friction. Kinetic friction depends on the normal force. The static friction does not, okay? The static friction, we think there's a formula like this, but there's not. This is the formula for the maximum value of static friction. And we're nowhere close to the maximum value here, okay? Okay, let's move on. I think I mentioned earlier that this tutorial I call the mother of all tutorials. If you were ever going to cry during a tutorial, this was it. So I just want to help us feel comfortable with that tutorial and go through what we experienced there. You remember that this hand was pushing with a constant push, always the same. And the table was frictionless. And we have enough experience with frictionless tables that we know if we push, it's going to accelerate. And so everything's accelerating to the right. And I'm going to put a number to that. Let's say that's 3 meters per second squared, just so that we've got a number there. Okay. Now, we were asked to draw free body diagrams for block A, the rope, and block B. And we're told that it's a heavy rope. This is page 1. Now, folks, I want you to put your pencil or your pen down, because the free body diagrams that I'm going to put up here are not only wrong, but sick and wrong, okay? They are the free body diagrams that most people start with, okay? This is what people do. They say, oh, on A, the weight's down, the table's pushing up, oh, and the rope is pulling. For B, the weight's down, the table's up, and the rope is pulling, and the hand's pushing. And then we say, well, if if the rope is pulling on A, then A will pull on the rope. And if the rope is pulling on B, then B will pull on the rope. Oh, and it's a heavy rope. Okay? Now, ideally, we would be doing this tutorial in person in a group of 4 students, and a TA would be there working with you. And if that were the case, I would hope that the TA would come by and say, oh, remember, this whole system's accelerating to the right. And that screams to the right. And I guess that screams to the right if this is longer than that. But that doesn't scream to the right. And then you, of course, would fix that. Watch, here you go. We're going to fix it. All better? Yeah, and then I hope the TA would say, well, yeah, that screams to the right, but what about this big scream down? And then, with a smile on your face, you would say, let's fix it. Pow! Okay? And at this point, I hope that the TA challenges you to label that force. What boogeyman exerts that upward force? Remember, all macroscopic forces are exerted by some thing that you can taste, smell, touch. What thing is responsible for that force? And if you can't find a boogeyman to blame it on, yes, sir.
Is it tension?
Is it what?
Tension?
Oh, I've already got the tension from A and I've got the tension from B. I only get one tension at each surface. But you are right, it is tension. But it's not up, okay? I can't find a boogeyman for that. But I do see that for a heavy rope on a frictionless table, no matter how fast you accelerate it, you're always going to have sag in that rope. And a rope can only pull in the direction of the rope. And so that means that A and B are going to pull up on the rope where they contact the rope. And this contact, or this upward component plus this upward component are going to balance out the weight of the rope. Okay? Now, by third law, if A is pulling on the rope up and to the left, the rope must be pulling on A down and to the right. Okay? Now I have a question for you. Is the normal by the table on A equal to the weight of A? Not anymore, no. It's got to screen balance in the Y direction, so this has to balance this component plus the weight. And so that normal force has to be bigger than the weight. Does everyone see that? Okay. Now, the same thing is true over here. If B is pulling up and to the right on the rope, then the rope is pulling down and to the left on B. And that means that this normal force has to be bigger than the weight. And we said that the hand had to be pushing bigger than that. Okay. Those are the correct free body diagrams. Those are the diagrams that I would hope that you would end up with after discussing with your group. Okay. Now, then you turn to page 2. And page 2 was the most challenging page of this tutorial, and that's where we spent most of our time. And what we did in page 2 is we waved a magic wand and we magically changed this heavy rope into a light string. But we were told that we were going to push so that the motion was the same. And by that we mean if it was accelerating to the right with 3 meters per second squared acceleration, it still is. Okay. So what does that say about the force by the hand? If I want this system to speed up by the same amount, but now I've got less mass, A's the same, B's the same, but the rope now is a tiny little string. Do I have to push as hard as I used to? No. Okay. If you want to speed up a Cadillac and a Volkswagen the same amount, you got to push harder on the Cadillac. It's that simple. Okay. So these are the free body diagrams for the rope. How many different changes can you find when we switch over to the light string? And this is the way we're gonna count them. Okay, this force is gonna change. That's one. That one gets smaller. If a force has components and this one changes and that one changes, we'll count that as two changes. But if this one changes, but this one doesn't change, that's just one change, okay? So, with your neighbor, decide how many changes you can see in those three free body diagrams, and then use your clicker to vote.
Logan.
Like, there's something.
So that will be takes.
I got 9. I don't know.
They just changed.
Isn't it writing downwards, so.
Not necessarily, just the vertical components of the, so this on the road is exactly what you need to counteract any of the changes.
Thing is. In there too.
They have to point farther. It's still less about weight though itself and more, you know, there's.
If you lessen that one. Yeah.
Okay, go ahead and get your vote in. Last call. Okay. Whoa, we're all over the map. Okay. Well, let's count them. Let's count them. Let's start over here on the easiest of the free body diagram. What about the weight of A? Was it changed? Heck no. Diet or exercise. Okay. What about this component right here? Yes or no? That's one. Okay. What about this one here? Yeah, that's two. If this one gets smaller, that one gets smaller. Okay. What about this one here? Does it change? Yes or no? Shout it out.
Yes.
If you say yes, raise your hand. If you say no, raise your hand. Okay, we're of two minds here. When you're trying to reason a dynamics problem, your best bet is to point at the free body diagram and use Newton's second law. If I'm looking at this free body diagram that represents block A, the mass of block A is not changing. We're told that the whole thing's still moving at 3 meters per second squared. And that means the net or total force on A has to stay the same. Well, the total force, if this plus this cancels that, this component is the total force. That is the net force. So this one cannot change. Cannot change. Check that your neighbor understands that. That's important.
And now,
You changed. You changed them.
Okay,
That's what it is.
let's keep counting. We've got 1, 2. What about this one here? That's 3. What about that one? No, if this one can't change, that one can't change. So I'm up to 3. What about this one?
Yes.
Yeah, that got smaller because we've got a light string. That's 4. What about this one? Okay, we're up to 5. Now, folks, unless someone asks you to marry them today, my next question is the most important one you're going to hear all day. Does this one change? Yes or no? Shout it out.
Yes.
Heck yeah. Heck yeah. Okay. Well, wait a minute. This one didn't. Why would this one? Well, again, we use Newton's second law.
With anything.
The acceleration of the rope or string doesn't change. That stays 3 meters per second squared. But the mass of the rope suddenly changed to a tiny, tiny mass of a string. And that means that the net force has to get smaller. I don't need as much net force to accelerate a tiny string as I do to accelerate a heavy rope. So this one has to get smaller. So we were 5. This makes 6. We're up to 6. Let's move. Is everyone okay with that? Yes, sir.
What were the first 2 changes?
What's that?
What were the first 2 changes?
The first 2 was this one and this one. Well, if this gets smaller, I don't need as much upward force to support them. Okay. So if this gets smaller, this one gets smaller. And so that's 2, that's 3, that's 4, that's 5, that's 6. Okay. So let's go on. We're almost done. If this one changes, this one changes, that's 7. If this one changes, this one changes, that's 8. If this one changes, that one changes, that's 9. And if this one changes, that one has to change to give me the same net force on B. So the answer is 10.
All right.
See if your neighbor got 10. If not, slap them. Do what you need to do. Okay.
Later.
Now, the next thing we did after we turned this heavy rope into a light string was we went another step and changed it into a dental floss. It's kind of comical. I was at my dentist and he asked, when was the last time you flossed? You should know, you did it. I'm sorry. My dad's a dentist, I know better. Okay, so we changed it eventually to a massless string. And for a massless string, oh, first of all, can you see all the changes with PowerPoint? PowerPoint's so wonderful. There's all 10 of them. Okay, and then when we go to the massless string, we don't have anything down here. And so we don't need any upward components. And what we get are the free body diagrams we started with, except we started with a weight force, and that's what made it wrong initially. Now, nearly every textbook that I know of for this class always assumes a massless string in every problem, okay? And they just assume that we recognize that a massless string would only have one tension, that the pole on one side of a massless string has to be the same as the pole on the other side of a massless string. It doesn't have to be 0. It can be 1,000,000 newtons on this side as long as it's 1,000,000 newtons on that side. Now, this approximation of a massless string makes sense. Usually the string is pulling a heavy block and the mass of the block is so much bigger than the mass of the string that it doesn't make sense to worry about the mass of the string, okay? Now, in the past, I have encouraged you, implored you to start every problem with a free body diagram of everything in the problem. But now I'm going to change that. Now I'm going to encourage you to draw a free body diagram of everything in the problem that has mass. Never again draw a free body diagram for a massless string. The reason is, first of all, it's boring. It always screams balance. But the real reason is it's confusing. I expect my free body diagram to scream the acceleration. This one screams to the right. This one screams to the right. This one screams balance. A massless object will always have a free body diagram that screams balance. Because if you look at F net equals ma, it doesn't matter what your acceleration is. If you multiply that by a mass of 0, you get a net force of 0, right? Okay, so this is just always going to be a confusing free body diagram. Now, it's been my experience that some people understand this better if we have numbers. And so I've made up some numbers here. And what we see here is that the net force on A is 5 newtons. What's the net force on the rope? Tell your neighbor real quick. What's the net force on the rope? Shout it out. 3. And actually, you should say 3 newtons to the right, because I got 8 to the right, 5 to the left. That's a net of 3 to the right. And the net force on B is 4. 12 to the right, 8 to the left is a net of 4.
The net force is not the same as the total amount of forces acting.
It is the total amount of force
The net,
as I add them as vectors.
yes,
As vectors. I can't just say 8 plus 5 is 13. No, no, no. It's 8 to the right, and then I'd have to subtract 5 to the left. That's the net. That's the net. How much more you've got in this direction above what you've got in the other direction? Okay, a question back here?
Sorry, I can't remember. Why is it 8 newtons to the right and then?
What's that?
Why is it greater?
Oh, because we found with the hand pushing on a frictionless table that everything was accelerating to the right. So my diagrams have to scream in the direction of the acceleration, because the net force is what causes that acceleration. Okay? Okay. Yes.
The string was attached halfway up the block, or off of the block. How does it attached to the bottom?
Oh, actually, interestingly enough, myself and Mark Summers were the first people to take this tutorial into a classroom. And we came back to Lillian McDermott and Peter Schaefer and we said, oh man, that was hard. That was hard. And I suggested, why don't you just take that rope right down to the bottom, let it just drag along the floor. It'll get rid of all the angles and make this so much easier. And I remember Lillian looked at me and she said, it's the mess that makes it fun. And really, this tutorial is all about practicing with Newton's second law and Newton's third law. Okay, so question back here.
Question again?
Oh, the rope has mass, and so if I want to accelerate it to the right by 3 meters per second squared, I got to pull harder on one end than I pull back on the other end. I need a net force on that. But we're going to see that when we go to the massless string, we don't get a different tension force.
I think it's like a mass.
Oh, because they don't have the same mass. F net equals ma. The A is the same, but the mass is different. And I just made up some masses here. Okay, A has more mass. You can see that its weight's bigger than B, and so I just made up some numbers there. Now, if we go from here to the light string, I still need 5 newtons of net force to accelerate A, because it's still the same mass, same acceleration. I still need 4 newtons of net force to accelerate B, because it's the same mass. But I don't need 3 whole newtons to accelerate this light string. Maybe just 1 newton, okay, is all I need. And then if I go to the massless string, I still need 5 newtons to accelerate block A. I still need 4 newtons, 9 minus 5, to accelerate B, but I don't need anything to accelerate a massless string. There's nothing to accelerate.
The tension force, the downward tension force always shared equally between the two sides.
No, and we just do not want to go there. That is one of the most difficult problems that that you could throw at a graduate student on their doctoral level exam. You just stay away from that one. Yeah, that'll be on the exam tomorrow. No, no, I'm kidding. No, never. Okay. How are we feeling about this? Do the numbers help? Okay. So let's go to this pretest that you took on Tuesday. You remember this table had friction, okay? And we're pulling this system across the table such that it speeds up to the right, Now you were asked to compare this question, the force exerted by string 1 on book A is less than, equal to, or greater than the force exerted by string 2 on book B. And you all answered this. Let's use our clicker to share our answers. Could I get some helpers? Where are my helpers over here? Thank you so much. Thank you. Helpers over here. Thank you. All right. Appreciate it. Mr. Rogers says always look for the helpers.
That's one of the.
I've done a year.
Okay, last call. Get your answer in. That all of us? Okay, good. The answer is greater than. It's greater than. Now, I did not collect this pretest because I've got tons of these. Over the years, over the 30 years that I was teaching this at Montana State, 31 years, I would collect these pretests and I had file cabinets filled with them. And I would read through them looking for common mistakes that people made, trying to figure out what it was that was making people stumble on this question and get it wrong. And what I found was discouraging. There were an infinite number of ways to get this wrong. But then as I looked more carefully, I found a pattern. And I found that those people that got it right tended to have a free body diagram drawn on their page. And those people who did not get it right did not. So if we want to compare the tension in string 1 to the tension in string 2, one thing to try would be to draw a free body diagram of something that is being acted on by both of those strings. And that's going to be book A. If I draw a free body diagram for book A, I've got weight down, the normal up. I have string 2 pulling back on A. I have the friction of the table pulling back on A. And I have string 1 pulling to the right on A. And I know that this book is speeding up to the right. So this diagram has to scream to the right in the direction of the acceleration. That means this tension in string 1 has to be bigger than both of these added together. So the tension in string 1 has to be bigger than the tension in string 2. Now, wait a minute, Greg. I think you cheated. We were asked to compare the tension by string 1 on A to the tension by string 2 on B. Not on A, but on B. Right. But I know it's a massless string, and I know that the force, the pull on both ends of a massless string is exactly the same. The force it's pulling on B is the same as pulling back on A by the law of massless string. Talk to your neighbor, see if your neighbor understands the answer to this question.
Because the string is massless, so we essentially say that is tension of string.
Just.
Just say that that force is being acted directly on A by B and B on. I'd like to keep that as a contact force,
Somewhere that
and A and B don't touch each other.
Or to make the entire thing
I
start.
think it's less confusing.
It's good to.
Okay,
That is okay.
again, when you're comparing forces, the best thing to do is to draw a free body diagram and point intelligently and say, that's got to scream to the right. And the only way it can scream to the right is for this force to be bigger than those two. Okay, that's the reasoning we would use. Now, suppose I went down to Lowe's and I bought 3 identical cinder blocks and I hooked them to 2 massless strings in these 2 configurations. Answer this question. The tension in the left string is less than, equal to, or greater than the tension in the right string. So I'll get you started. You can click.
Oh my God, wait. Okay. No. Good. Rate is less. Because even though. Twice as much. That's right. Yeah, well, no, that's.
Okay, last call. Okay, equal to is the correct answer.
Yes, I think you're right.
Now, how do I justify that?
Don't know how.
Again, the best way to argue a dynamics problem is with a free body diagram. If I draw a free body diagram, I put the weight, let's say that's a 50 Newton cinder block. And it's not going anywhere, it's just sitting there. So the tension force by the string on the block, also by Newton's second law with 0 acceleration, must be 50 Newton. My question, which cinder block did I draw the free body diagram for? All 3, all 3. And so that means that the tension has to be the same in both of those strings. Now, if we think about what tension is, one way to measure it would be to insert a spring scale and just see what the reading is on the spring scale as the string is pulling on both sides of the spring scale. Now, if I take a spring scale and hold it to weigh a fish, I hook the fish on that little hook at the bottom. That fish pulls down on the spring and gives me a reading. Well, I'm pulling up on the scale, but the scale's not measuring that. It's measuring how hard the fish is pulling down on the scale, okay? Now, whether I hold that or whether I tie it to the ceiling and let the ceiling hold that doesn't matter, okay? The same thing's true here. Whether I use a wall to hold this in place or whether let's say I get rid of this block and I'm just holding the rope right there. That's not going to change the tension in the string. So with me holding the rope right there, I could also just use another block to hold the rope right there, or I could use the wall to hold the rope right there. It's all the same. It's all the same. So draw a free body diagram is my message to you on that. Now, this is an old exam question that was given many years ago. And what we've got here is a block A that weighs 50 newtons on a frictionless ramp. And we find that if we hook it over a massless pulley with a massless string, that block B will pull it up that ramp at a constant velocity, Now, when you see constant velocity, you want to ding, 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 zero acceleration, equilibrium, balance, okay? So the first thing we want to do is draw free body diagrams for A and B. So get going on that. Which one should you start with? Which one should you draw first? B. We got a little bogged down on the tutorial, so in the interest of time, let's do this together. With B, I put the weight force, Earth on B, towards the center of the Earth. I then ask, are there any magnets in this problem? No. What touches B? The string, and it pulls with a tension force. And I know that this diagram has to scream balance. So these two are equal to each other. By what law? By second law with zero acceleration. I then draw the free body diagram for A. I have the weight force, Earth on A, and I'm told that that's 50 newtons. The only two things touching A are the string, and it pulls up the ramp. And the ramp pushes with a normal force, but no friction. And so that's my free body diagram for A. Now, whenever I have a ramp problem, I rotate my coordinate system so that the x-axis lines up with the ramp. And that means that my normal is lined up with the y-axis, my tension's lined up with the x-axis. It's always the weight that I've got to break into components. And I always do that, folks. I want you to do it this way. Look in the direction of the normal force and go the other way until you can make a 90-degree turn to get to the end of that weight. If you do it that way, this angle between the Y part of the weight and the total weight will be the same as the angle of your hill or ramp. Now, this is a 3, 4, 5 triangle. Okay? And so this is going to be 3 times 10. This is going to be 4 times 10. And this is 5 times 10. 3, 4, 5. Now, once you've broken the weight into its components, you throw away the original and use the parts. Well, again, this is going at constant velocity, 0 acceleration. This has to screen balance in both the Y direction and the X direction. Y direction, I've got one force in the positive Y direction, one in the negative Y direction. This has to be 40 newtons. In the X direction, I've got one force in the positive X direction, one in the negative X direction. This has to be 30 newtons. Because this is the other end of the same string, this has to be 30 newtons. And because this diagram is balanced, this has to also be 30 newtons. And that makes the mass of B 3 kilograms. Now, when I put this on an exam, it was tragic. I graded late into the night, and what I found over and over again were that people got the right answer and then erased it or crossed it out because they said, oh, if B is only 3 kilograms and A is 5 kilograms, a little one can't pull a big one up the ramp. Well, let me show you that it can. I have here a cart that has a mass of 502 grams, and I'm going to pull that up a ramp. And I've just got 40 grams here. Just 40 grams is all we've got. And what you see is that that's pretty balanced. And if I get it started, it just goes at constant velocity. Okay, it just, let me get it started here. Oh, did I lose one of my masses? Yes, I did. Oh, you can do this. Oh, man. Oh, hush. Okay. There we go. Okay. Now, what we see is that it doesn't have to balance all the weight, just the X component of the weight. Indeed, if I were to take away the ramp and make this perfectly horizontal, I could put a huge mass on here as long as it was a frictionless table, and with a teeny tiny little mass hanging off the end, it would accelerate. It wouldn't be a big acceleration, but with no friction to the right, it would accelerate to the left. Okay, see if your neighbor's on the bus with that. Okay, another clicker question. Suppose while A is going up the ramp, a hand comes and stops it. And then the hand lets go. After the hand lets go, will the block A move up the ramp, stay put, or move down the ramp? With your clicker, please. Go ahead and click.
This is a diagram.
I don't know.
Okay, sorry, 0. So if it stops, that will. There's no net for that unit. Stops.
Okay.
Fine.
Last call. Okay, we're all over the map, but the answer is B, stay put. Why? Well, if it's going at constant velocity, zero acceleration, my pre-diagrams are balanced. When the hand lets go, I go back to those free body diagrams where everything's balanced. Now, zero acceleration can mean 5 miles an hour up the ramp, but it's a constant 5 miles an hour. Or it can mean stop, and it stays stopped. Those are both zero acceleration, okay? And my free body diagram would be balanced in both cases. Now, to review for the exam, I only need 2 slides. That's because we're doing the same thing over and over again, okay? For every force problem, we draw a free body diagram, and then we use Newton's second law in the y direction, and then we use Newton's second law in the x direction. And that's it, over and over again. And I hope during this exam that you're just giggling, that eventually they come and want to kick you out of the testing center because you're giggling, because you're just doing F net equals MA over and over again. So here I have a mass of 24 kilograms accelerating to the right by 6 meters per second per second. And I've given you some of the forces, but not all of the forces. I haven't given you F3 or F5. So first, what is F3? With your neighbor, figure out F3 and use your clicker to let me know.
Wait, it's not.
Sorry.
Down here now.
Minus it.
70. Be less than.
Cause that's one is.
No acceleration.
Doing a little too much work.
I didn't touch this. All we need to do is find it.
Bound.
Five. It's unbalanced.
Uh-huh. Oh, wait, it goes.
Over there were.
Just like.
Statics is kind of stick. That was from a piece. I mean, it should be hard to hold, but I mean, I know.
Okay, last call. Get your vote in. While you're getting your vote in, let me remind you to bring scratch paper to the exam. Again, there's 750 students in this class in the 3 lecture sections, and we didn't want to print the exam 750 times. So you'll need to draw your free body diagrams on your scratch paper. Okay, last call. Have I got everyone? Good. The answer is C. Very good. And again, we just use Newton's second law. I add up all the forces, but I add them as vectors. The 140 is up, so it's positive. The 630 is up, so it's positive. The 240 is down, so it's negative. And the F3 is down, so it's negative. And the acceleration in the y direction is 0. So this has to scream balance. And that gives me 530 newtons. Well, now let's find F5 with your clicker. This is a little more challenging, but not much.
Sorry, I'm so confused.
As long as that does make sense. Yeah.
Okay, last call, get your vote in.
I wanted to kind of get the.
Okay, good. The answer is B. We are doing well. We are doing well. Well, now F net is equal to M times A. The mass in kilograms, the acceleration in meters per second squared. F net is I just add up all the forces in the X direction, but I add them as vectors. 890 is to the right, so it's positive. 710 to the right, so it's positive. 420 is to the left, so it's negative. F5 is to the left, so it's negative. And when I solve that for F5, I get 1036. Okay? Now, we've got 10 minutes, and that's enough time to talk about this gauntlet problem. Okay? I just want you to see the answer to this gauntlet problem. You've all worked it, I assume. You've tried to get to the bottom of that page. Well, remember, the table's frictionless, and the hand is pushing on A. And we're asked to draw free body diagrams, and we're told that the mass of C is 3 times the mass of A, and the mass of B is twice the mass of A. And so the vertical forces, I've got little weight on A, I've got twice the weight on B, and 3 times the weight on C. I start with the free body diagram of the simplest object, that would be C. The only thing touching it besides the table is B, and it pushes. Okay? Now, if B is pushing to the right on C, C is pushing back on B, equal and opposite by Newton's third law. The only other thing touching B besides C is A, and it pushes. Now notice I put this force bigger than the force to the left, because that diagram has to screen acceleration to the right. It's speeding up to the right. Now, if A pushes to the right on B, B pushes to the left on A. By third law, those are companions. And finally, the hand pushes on A. Now, if I were to tell you, this is not in that problem, this is extra. If I were to tell you that this force right here is 15 newtons, could you find the magnitude of the other horizontal forces?
Yes.
Tell your neighbor what they would be.
Said if the normal
Right.
well, he's pushing on it, so we'll see.
Okay,
Right, they shouldn't.
let's talk about it. We use this reasoning in the tutorial homework, tutorial 4. I need to use the idea of the net force. The net force on C is clearly 15 newtons. And they're all moving together, so they have the same acceleration, but they have different mass. Since A has 1/3 of the mass of C, the net force on A would only be 5 newtons, and the net force on B would be 10 newtons. Okay, everyone see that? Well, now I'm ready to figure out the size of the other forces. If B is pushing on C with 15 newtons, by third law, this is also 15 newtons. This diagram for B has to scream it has to screen to the right by 10. And so that means this has to be 25, because 25 minus 15 is the scream of 10. If A is pushing on B with 25, B is pushing on A with 25 by third law. This diagram has to scream to the right by 5, so the hand must be pushing by 30,
Give us the ratio.
because 30 minus 25 is a scream of 5. That makes sense? That speak to your soul? Okay, good. Now, remember, as we went down that gauntlet, more and more people fell off the bus. Yes, sir.
How did you find the 3 net forces on the bottom?
How did I find the what?
The net forces, the 5.
Oh, F net equals M times A. They all have the same A. But the mass of C is 3 times as big as the mass of A.
That was given.
That was given in the problem, yeah. And mass of B was twice the mass of A.
Thank you.
Okay,
That.
now, in the rest of this problem, we replace the massive block B with a much less massive block D. And we were asked some questions about that. The first question we were asked is, what happens to the acceleration of the blocks? Well, if I lump these all together as one unit, A, B, and C, our free body diagram doesn't have any of the internal forces. It doesn't have the force of A on B or B on A or B on C or C on B. If we draw a free body diagram for Greg, we don't draw Greg's liver on his spleen or his spleen on his liver, and I don't even know if those are close to each other, okay? We just draw external forces. The floor on Greg, the earth pulling down on Greg, okay? So it simplifies our diagram. Now, if we look at the diagram for A, D, and C, you see there's less mass, so these forces are smaller. But we're told that the hand pushes the same. That was given in the problem, okay? So if we use Newton's second law, F net equals ma, the net force is the same. That's the push by the hand. But now the mass is smaller, so the acceleration has to be bigger. If the acceleration was 3 meters per second squared, it's got to be something bigger than 3 meters per second squared when I reduce the mass of the system. Again, you push the same on a Volkswagen and a Cadillac, the Volkswagen speeds up more. Everyone okay with that one? Well, now we're asked to just look at the net force acting on block C. Just block C. So if I use Newton's second law here, the mass of C stays the same, but now it's got a bigger acceleration. And so that means it has to have a bigger net force acting on it. Well, you remember the free body diagram for block C was pretty simple. It had the weight down, the normal by the table up, and it had whatever was behind it pushing on it. And you see that if I have to have a bigger net force in this situation, the little block D is pushing harder on C than the big block B. That surprised some people. Some people were thinking, oh, a bigger block should push harder. That's the way it is on the playground, okay? But no, if I have to have a bigger acceleration here, I have to have a bigger net force. Okay, questions on that? We're almost to the bottom of that page, so close. The last question asks us, which is bigger? The force by C back on B or the force by C back on D? And that's the one that only a handful of students got right out of a class of 350, okay? Tell your neighbor, which one's bigger? Which one's bigger?
So ABC left to right.
On the yellow.
What is D?
Okay,
See?
if you believe Newton's third law, we've already answered this question. You remember, we compared these two forces just a minute ago. This was B pushing on C, and this was D pushing on C. And we said that the little block was pushing on C bigger than the big block. Well, by Newton's third law, this is the same as that. You see, they're both normal forces. This is D on C, this is C on D. The indices are switched. This is the same as that. So if this force is bigger than that force is bigger than that force. Okay? Follow it?
Yes.
Check that your neighbor's on the bus, people. One last buddy check. Folks, may the net force be with you when you take that exam. Remember that I love you.
Finding enough problems on
Remember your name. Right.
Gotta get this done.
Then,
Is there a late?
okay. When I get to. Good luck.